Let's talk about mass balances that don't have any reactions. Let's say you show up to class and someone has placed something horrible in the trash can. The entire room stinks. Being a conscientious person, you immediately throw the offending item away outside, but the odor still lingers. How long is it going to take to dissipate? We can model the room as a continuously mixed flow reactor to solve this problem. After watching this video, you should be able to model various systems as CMFRs and solve problems in unsteady state or transient systems like this. So let's go back to our stinky room. First, we can draw the system. Our system is going to just be the room, and this room is ventilated, so there is non-stinky air flowing into the system and air is exiting our system to balance. For each stream, we need a volumetric or mass flow rate and something that tells us about the concentration of the stink. For our purposes, we'll say the stink is due to H2S, hydrogen sulfide, which is a rotten egg smell. H2S has an odor threshold of 0.47 ppb. This means that if the concentration is below that, you can't smell it. Our starting concentration in the room, let's just say, is 7.2 ppm, and the ventilation system blows clean air into the system containing no H2S. So under these conditions, the H2S concentration in the room will slowly decrease, even though we're not thinking about any sort of chemical reactions that could be occurring. Once the concentration is below the odor threshold, we won't be able to smell it anymore. So let's say our room is 3,500 cubic meters in volume, and ventilation exchanges the air in the room 6 times every hour. So in this flow chart, I've given only one variable for the inflow and the outflow of the room, V dot. We don't want air accumulating in the room because that would cause an increase in air pressure, which isn't something that we would want. So these two flow rates are going to be the same. Because we're assuming that the room is a CMFR, the concentration at every point inside the room is the same. Therefore, the concentration leaving the room will also be the same as the concentration inside the room. On the flow chart, I've said that CT is 0.47 ppb. And in order to solve our problem, I have to find this time t. So how long does it take for our room to reach a concentration of 0.47 ppb? But before we worry about hydrogen sulfide, let's start with the easier problem. So what is V dot? We know that the room does 6 air exchanges each hour, so we can use this information to solve for V dot. So here, what we're going to do is we're just going to multiply the volume of the room by 6, and we end up with 350 meters cubed per minute. You've probably already noticed that our room is not at steady state, so we're going to have to solve this problem a little differently. You've probably already guessed that we're going to be doing a mass balance on H2S. So we'll start with our general mass balance equation. But I'm going to eliminate the in term because we don't have any H2S flowing in. The concentration is 0 coming into the room, and we're eliminating any sort of reactions. So basically, the accumulation is going to be, term will be negative because we have mass only flowing out of our room. Okay. So what we need to do now is we need to come up with expressions for the accumulation term and the out term. So our accumulation term is going to need to tell us how the mass is changing over time. We're working with concentrations here, so we can look at how concentration changes over time, which is dc dt. And then in order to get mass, we'll have to use a term for V, or we'll have to use the volume of the room, V. So our m dot term is going to be the mass flow rate of H2S out of the system. We're going to multiply the volumetric flow rate of air out of the room by the concentration of H2S in the room. Now we need to do some calculus to solve this equation. So dc dt times v, the volume of the room, equals negative v dot times c. We'll do some rearranging, put all of the concentration terms on the left side, all of the time terms on the right, and we'll pull those constants v dot and v out of our integral. Before we complete this equation, we need to choose our boundary conditions. Here we look to the problem. So we know that at time 0, the starting concentration is 7.2 ppm. This starting concentration is also often called C naught. And then we're looking for the time at which the concentration reaches 0.47 ppb or 0.00047 ppm. We're going to call this time T and the concentration at that time CT. So those are going to be our bounds, and we can go ahead and solve this equation. Finally, when we look at this equation, we see a term for flow rate, volume per time divided by the volume, V dot over V. This term comes up a lot in these types of equations, and it's related to the residence time of the system, or tau. So the residence time is the amount of time a theoretical particle would spend in your system, and tau equals V divided by V dot. So for our system, we can calculate our residence time by dividing the volume of our system by the flow rate, and we end up with 10 minutes. This makes sense because we have 6 air exchanges per hour, so the average particle would remain in our system for 10 minutes. So we can rewrite this equation as CT equals C naught times e to the negative t divided by tau. We plug in our C naught and our tau and then solve for CT. Before I do that though, I want you to visualize how the concentration of H2S inside the room changes with time. I'll use a spreadsheet and plot time on the x-axis and concentration on the y-axis, and you can see that we have this exponential decay of H2S in our room with time. And again, this is just due to the ventilation system blowing the H2S out of the room. So even with no reactions, the H2S drops very quickly. And you can also use this equation to figure out how long it will take to reach 0.00047 ppm, and that's going to be 96 minutes. So while the students in this class are going to have to deal with the horrible smell, it should dissipate during the next class period. So this is one example of how to model a transient CMFR system. You can apply the same type of analysis to many different systems to estimate how pollutants accumulate or dissipate in an environment.